concept of displacement current and Ampere-Maxwell circuital law. In 1920, a prominent scientist, Hans Christian Ørsted, observed a phenomena which was almost accidental. In his laboratory, he saw that a compass was being deflected. There was no reason for it to deflect, but when he observed that a current wire was kept near this compass, he questioned that is this thing causing the compass to get deflected? He took the wire far away from compass, and the compass came back to its original state. And when he brought it back to the compass again started deflecting. Before 1820s, electric phenomena and magnetic phenomena were believed to be separate and not interdependent. But after observing this, Hans Christian Ørsted formulated that current can indeed bring an effect to the magnetic field or magnetism. Here you can see that Christian Ørsted is demonstrating. Here is a compass needle, and he has kept this current wire above this compass, and he's demonstrating that as the current is flowing through this wire, this compass is getting deflected. This was a major breakthrough in physics. And after that, after Ørsted released his paper, André Marie Ampere became obsessed to study how current affects the magnetic field. André Marie Ampere started experimenting, and he saw that magnetism is nothing but current in motion. As the current flows, it generates magnetic field. Magnetic effects arise due to moving charges. This was what Ampere said. But he just didn't want it to put out a theory or definition. He wanted a concrete mathematical law that could show the relation between current and magnetic field. And that was when he formulated the famous breakthrough in physics, which was known as the Ampere's Circuital law. The left-hand side of this equation contained the line integral of the magnetic field, whereas the right-hand side contained a constant multiplied by current. Let's understand what this equation says. Suppose we have this current wire which is carrying some current. Say I enclosed. I enclosed means the current that's flowing inside this. And if this current is flowing, then a magnetic field is being produced around this wire. Now the left-hand side of the equation says that if we add up all the magnetic field around this length L, every magnetic field that is being produced around this wire, if we add it up, then that must equal to the current that's flowing inside this wire multiplied by a constant mu naught. So this was what Ampere formulated. But later, Maxwell realized that his equation fails for time-varying electric fields and corrected it using the concept of displacement current. So we read that Ampere's circuital law says that if a current is flowing through this wire, suppose the current is I, then if we add up the magnetic field which is being produced due to this flowing current, and we add the magnetic field around this whole length of wire, then that must equal the current that is flowing inside this wire. This is what Ampere's circuital law said. Another form to write this is like this. Here this H means magnetic field intensity. Well, the major difference between B and H is simple. B is the total effect of magnetic field due to current as well as the property of the material. But B tells us about the magnetic effect only because of the current that's flowing. It does not include the effect that is produced because of the material. So the more accurate way to write Ampere's circuital law is like this, because Ampere did not account the material effect we may use this or this, but the main thing that we observed from Ampere's Circuital law was that the magnetic field or the magnetic field intensity was directly dependent on the current that's flowing in this wire, which means that if the intensity of current gets increased, then the magnetic field will be of higher intensity, and if the current intensity is decreased, then the magnetic field intensity must also decrease. Now let's take consideration this equation. We write it like this. Now we know that the relation between B and H is like this. The original relation between B and H is this, but this magnetization becomes 0 for a vacuum. So this equation can then be written like this. Hence B upon mu naught is equal to H. Hence this equation can be written like this. Now since to the right hand side we have current, we know that if the charges are crossing through a surface S, then current can be represented as the total number of charges crossing this surface, which is represented by this, where the integral shows the addition of all the charges that are passing through the surface, and J represent the current density, and the current density is simply produced because of the charges that are flowing through the surface. Hence this equation can be written like this. Now to the left hand side we have a line integral, and to the right hand side we have a surface integral. Now we must convert the line integral to surface integral to equate the two sides of the equation. Hence the line integral can be converted into a surface integral using Stokes' theorem. What does Stokes' theorem says? Stokes' theorem says, suppose we have a line integral AdL, then in order to convert it into a surface integral, we must put a curl of this and write like this. This is how Stokes' theorem works. Hence this can be written like this. So we simply took the curl of H and we get the left hand side expression like this. So now we can simply equate these two equations. Since the integrals are same on both the sides, hence we can remove them and compare these quantities. So we get curl of H is equal to J. This is an important equation and we must remember it, because this is where the Ampere went wrong. But how did he went wrong? Let's study about that. We know that equation of continuity says that divergence of J is equal to negative of rate of flow of charge density. And like in this equation we found out that curl of H is equal to J, like current density. So here we will substitute this. In place of J we will put curl of H. On doing so, this equation becomes divergence, and in place of J we put curl of H. Now we know from the vector analysis, divergence of a curl is equal to 0. The divergence shows if something is entering inside or coming outside, whereas the curl shows about the rotation. Hence the left hand side of the equation becomes 0. Hence this becomes this, which shows that the rate of decrease of charge density is equal to 0, which means that suppose this is a container and the charges are moving outside, then there is a motion of charges outside of this, but it is not producing any current. So this is fundamentally wrong and is not obeying the equation of continuity. So if we went according to Ampere, then this was the equation obtained from his law. But if we use this in order to study the equation of continuity, we saw that it didn't upheld the equation of continuity well. Hence, for time dependent, i.e. where time is changing, the equation of Ampere's Circuital law must be modified, as it is violating the equation of continuity. What Maxwell suggested was that in this equation, the equation that we obtained from Ampere's Circuital law, he said that another term must be added to the right hand side with the current density, and he named it displacement current. So we add this quantity J dash, which is displacement current, to the right hand side. Now what is this? So in order to identify this, Maxwell said that we should take divergence on both the sides. On taking divergence, on the left hand side we get divergence of curl of H, and since divergence of any curl is equal to 0, hence the left hand side becomes 0, whereas on the right hand side we have divergence of current density plus the displacement current. Hence we see that divergence of J plus divergence of J dash is equal to 0. So we can take this to right hand side and it becomes minus of J dash. Now from the equation of continuity we know that divergence of J is equivalent to the rate of decrease of charge density. Hence we see that divergence of J means, so in place of divergence of J we can put this rate of decrease of charge density, hence the negative will cancel out, hence we get this expression. Now from the Maxwell's first law we know about this equation, which means the divergence of electric field displacement is equivalent to charge density. This is what the Maxwell first law says. This divergence shows that this electric displacement field is either going outside or is entering inside, and that is equivalent to the charge density, because it is the charges, a lot of charges, that must be falling inside or outside of place, causing the electric displacement field. Hence we can put this in place of rho here. Hence on putting divergence of electric displacement field in place of rho we get this. By using the identity of vector analysis we can take this divergence out and take this in. Hence the left hand side, that is divergence of displacement current, equals the divergence of the partial differentiation of the electric displacement field. Hence since the divergence is same on both the sides, so we can compare these, and hence like this we get our value for the displacement current. Hence we can put this J dash back into this equation from where we started, and hence we get this curl of H is equal to current density plus displacement current. Putting this here we get curl of H is equal to current density plus partial differentiation of the electric displacement field. So the displacement current is just produced by the change in electric field with respect to time. And here we must specify that this electric field is actually an electric displacement field, and an electric displacement field is dependent on the polarization of a dielectric. Hence this is the revolutionary equation which was modified by Maxwell, and this is what we call Maxwell Ampere Circuital law. Hence we can say that displacement current arises due to variation of D, where D is electric displacement field, the field that is produced because of the free charges. Hence this is how we found out about the displacement current and the Ampere-Maxwell law, and this has great application in capacitors. in case of capacitor, suppose a current is flowing, and here is one plate and here is the other plate. We observe that as the current was flowing, then according to Ampere law, the current must stop here, but the current was coming out from the other side, and we had no explanation how the current was coming out of the other side, whereas there was no connection in between. This phenomena was explained by what we study as the Maxwell Ampere law. It shows that the current that is flowing here makes one plate positively charged and the other becomes negatively charged, and because of this an electric field gets produced between these two plates, and this electric field is nothing but electric field displacement, or we can say D, which is depending on the polarization. This is the polarization, plus minus polar, right? The polarization of this dielectric. Hence, the current that was coming out side of the other side was due to the effect of the electric field that was being produced in between, and this electric field was producing the current that was coming out of the other side. And this is how Maxwell modified Ampere's Circuital law, which could now explain how the capacitors were working and why the current was coming out from the other side, even if there was no circuit connection between them.